name is Ziyaad, and today I'm going to be presenting on Magnon devices and Magnon microwave antennas. Okay, so first I'm going to provide a brief introduction to Magnons. We didn't really cover them that deeply in this class, but they were mentioned a few times in the guest lectures, so I'm just going to give a quick overview, and then I'm going to talk about three types of Magnon devices: Magnon propagation devices, Magnon logic devices, and then finally Magnon microwave devices. So first off, magnons are the quantization of spin waves, and they're quasi-particles in magnetic materials that are made of basically the combined spin states of the different particles in the materials. They were first theorized by Bloch in the 1930s, and here is a diagram of what that would look like. So you can see that each of the spins are aligned in such a way that they form a wave, and then these waves can have different wavelengths depending on the Magnon mode. The first device that I'm going to talk about is Magnon waveguides. So basically, in order to make magnons useful, we want a way to be able to control their movement. So what a Magnon waveguide does is that it combines magnons in two directions and allows them to propagate in the third direction. And this was originally done using YIG films in the early 2000s. And this image over here shows an example of some of the Magnon modes propagating along a waveguide. The next device I'm going to talk about is Magnon multiplexers. So once you're able to confine the magnons and transmit them along a certain direction, you want to be able to control their path. For example, a multiplexer can give you frequency selective control where different frequencies travel along different paths. And one of the ways this is done is with the inverse design method. The inverse design method basically it optimizes the material distribution in a grid using some gradient descent algorithm, and it decides whether or not a material should be placed in each of these boxes. And what this does is it allows for non-intuitive designs that couldn't easily be theoretically calculated by a human. The next thing I'll talk about is Magnon topological waveguides. So what this does is that it uses a topological insulator. In this case, it's ruthenium vanadate, and it confines the magnon to the boundary between two phases of the insulator. And this is important because it allows for a much smaller confinement width than other waveguide architectures. For example, in the past, wrong way. In the past, we see that this is an 800 nanometer width to the waveguide. And over here, these are 300 nanometers. But the barrier between topological insulator phases can be down to even a few nanometers. So this allows for much higher density networks if you want to transport multiple different magnons. Next, I'm going to talk about Magnon logic devices. So magnons can be used to do all the fundamental computing devices, such as logic gates and or not. And the way this was originally done was using a Mach-Zehnder interferometer configuration. Basically, there are two arms that magnons travel in, and there's a phase shifter. And based on the phase difference, you can manipulate the interference to get the result of your desired gate. So for example, this is a NAND gate, and this is the output time signal that shows that the gate corresponds to the NAND functionality. Then also Magnon transistors were developed. So these will follow the same configuration as a MOSFET with a gate, source, and drain. And these are very useful because magnons don't have joule heating, so they're much less power hungry than the traditional CMOS. And the way this is done is that the state of the transistor is controlled by a current through the gate, which through the spin Hall effect can control whether the magnons are allowed to propagate or not along the length of the transistor. Then I'm going to talk about the inverse design of Magnon logic gates. So this is relatively recent, and what's being done here is they're using the inverse design method I mentioned earlier to optimize the current through a 7x7 array of current loops on a thin YIG film. And what this does is it allows one device to be used as any logic gate based on the current input. And over here we can see the high accuracy of the results for a couple of gates that they demonstrated. Now onto Magnon microwave devices. So the first is a Magnon photon coupler, and this is basically a YIG sphere in a microwave cavity. And over here we can see this is the field distribution in the microwave cavity, and this allows you to couple microwave photons to the Magnon modes in the YIG sphere. So this allows you to induce magnons from a traditional microwave circuit. And I know I mentioned a lot of the past devices were all using YIG because it's a very high quality magnetic material and easy to fabricate. But recently there's been a push for this new CRSBR material because it has a very high magneto-optical coupling, and this can be important for quantum computing applications where you want to couple to qubits in an entangled system. Now I'm going to talk about Magnon microwave antennas, and I'm going to focus a little bit more on this one because it was designed in MUMAX, so it's very relevant to what we've been doing in this course. So this device was done with FEGA on lithium niobate, which is magnetostrictive on piezoelectric materials. So this works through phonon-magnon photon coupling, where they launch a surface acoustic wave, which couples to a magnon mode, and that couples to a photon mode and allows you to release a microwave. So what they did in the paper was that they simulated a surface acoustic wave by a time-dependent KU1 and a time-dependent field. And here lambda S is the magnetostriction of the magnetostrictive material, and sigma is the stress from the piezoelectric material, and this allows you to basically effectively reproduce a surface acoustic wave in MUMAX. And for example here, this is the effect of the transverse stress, and this is the result of launching the surface acoustic wave along the x-axis. And we can see that they're relatively single domain formations. So then the results of this design was that the spacing between an array of nanowires decides whether or not you can have a high quality single photon emission, which comes from a single magnon mode being excited. And they found that for in ideal spacing, the result is that all the nanowires have an effectively single domain configuration, and that allows a single frequency magnon to be present. And then from the magnon photon coupling, this releases microwave photons into the surrounding area. So this can be used as an antenna, and it allows you to interface your magnon systems with the external world. So I hope this gave you a general overview of what magnons are used for in modern technology and their different applications.